Hello everyone. This tutorial video covers the basics of layout design in Cadence environment and then doing post-layout simulation using HSPICE. The demonstration is done for a simple CMOS inverter. Caliber tool has been used for the DLC, LVS and parasitic extraction. So let's get started. So this is my virtual. Cadence is already open here. So let me open my library manager. So before doing the layout of the inverter, we'll be designing the schematic version of it. So let me select one library, demo library, and let me create a new cell view of the inverter. So yeah, so let me give us the name demo inverter. Click OK. So this is my schematic editor where I'll be designing the inverter. So let me add instances, the PMOS and NMOS. So create instances, click here. So I'll be using the NMOS and PMOS from the SCL library. So TS018_SCL_prime is my library where my PMOS and NMOS is located. So if you see here under the category of everything, NMOS_18 will be using the symbol. Close this library manager, close this one also. So just place the device and then press escape. So this is my NMOS. So let me edit the properties. So currently the gate width of this NMOS is 0.42. So let me make it as 2 micrometer. So just type 2. Here we don't have to type mu or u for micrometer. Only writing 2 is sufficient. By default it means 2 micrometer. Click OK. So now let me select my PMOS from the same library, TS018_SCL. So PMOS_18. So the 18 here, it means the supply voltage suitable for this device, or the maximum supply voltage this device can support, is 1.8 volt. So close this window again, press escape. So now then we will do the connection of the inverter. So two gates are connected and 2 drains are connected for the PMOS and the NMOS. So now again connect the bulk to the source of the PMOS, connect the bulk of the NMOS to the source of it. Now we need to edit the properties of the PMOS. So select it and press Q to get this edit object properties window. So here I will take the gate width as the double of what I have taken for the NMOS. So in NMOS I have taken 2 micrometer. Here I'll make 4 micrometer. So click OK. So now I have set the sizes of the PMOS and NMOS, and my connection is also done. Now I need to add pins so that I can apply the necessary signals. So create pin. So select here. So with my direction selected as input, I'll type as in and just hide it and just place it here and do the connection. Similarly, let me make my output pin, the direction selected as out, type out, do the connection. For ground and VDD, I'll use this name, VDD and GND, and the direction should be selected as input output. So place the ground here. To undo any comment, press U. So when the pins just overlap this way, it means that it is connected. If it is not overlapped like this here for the ground, you need to do the connection. So check and save. So my inverter is ready and we'll go for layout now. But before going layout, let me create this cell view for this schematic. So create cell view from cell view. So with the default setup, click OK. So top pin is VDD ground, right pin is out, left pin is in. I prefer this ground should go in the bottom. So just select it and press middle click to copy this ground in the as bottom pins, and then I delete from the top pins. Click OK. So now my cell view is created. Close it. So let's create the layout for this inverter. So click launch, open layout, Excel. So create new, I'll be creating a new, and let the configuration be set as automatic. Click OK. So with this default setup, click OK. So now this is my virtual layout suite Excel editing. So here I'll be designing the layout for the inverter. So before we start, there are certain things we need to follow. So this is the reason where I'll be drawing the layout of the inverter, where I'll be placing the devices and doing the necessary connection using the metal layers. So if you see on the left side of this editor, you'll be seeing the layer window where it will be showing what are the layers that I'll be using for designing the layout. So you can see the various layers here. So these are the masking layers for metals and the devices like that. So as we go further, this window will be more clear to us. So let's get started to make the layout. So similar to the schematic design, we need to get the instances. So create instances. So now I need to browse and go to the library, and we need to select the layout version of the same devices that we have used to create the schematic. So we have used nmos_18 and pmos_18 from this library ts018_scl_prime. So let me search my PMOS first, NMOS. So this NMOS_18. So I need to create the layout version of this device. So initially, while I was drawing the schematic, I was selecting the symbol version. So close this library manager, hide it, and you see something is attached to my mouse pointer. So just click the mouse, but still the device is attached. So just press escape ESC to undo this command. Now if I zoom it just by right clicking and dragging the mouse, I'll be able to zoom to this location. I'm seeing that there is something, but it's not visible. So to make it visible, press Shift and F. So you see my NMOS is visible. So there are certain commands that we should follow to help us editing. One is like zooming in and zooming out. So we can do it like zooming in, and view, zoom out, view, zoom out. Here the shortcut keys are also there, as for zooming in, Ctrl Z, and for zooming out, Shift Z. So if we remember the shortcut keys, it becomes easier and more handy to do the layout. To fit everything, to fit the entire design on the screen, you need to press F, like that. So there are some more other options, but mostly we'll be using zooming in and zooming out and fitting everything in the area by pressing F. Now I have placed my NMOS. Now I need to make this size of the NMOS similar to the size that I have taken in the schematic. So with this NMOS selected, press Q to get the properties window. So if in the parameter tab, you'll be seeing the parameter of this device. So since I have taken 2 micrometer for the NMOS, for the width of the NMOS, we'll take 2. The gate length is default 0.18, and it is same to the schematic. In the schematic also we have not edited the gate length. If you press OK, so you see the length of the NMOS has been increased from 0.42, which was the default width, and it has increased to 2 micrometer. So if I press F, the entire thing has been fit in the screen. Now I'll be zooming it out by pressing Shift Z, so that I can place the PMOS on the top of it. But before we go ahead, if you observe here, my mouse pointer is just moving from, if I zoom in here, it's moving from one grid point to the other grid point. Now here I need to decrease the resolution of this grid, because otherwise it may create a problem while I'll be drawing the metal layers. So to decrease it, go to Options, Display, or the shortcut key is E. So here we need to decrease the X snap spacing and Y snap spacing, so that this snapping between the grids decreases. So let me make it as 0.01 and 0.01. Make sure that you don't decrease it too low, otherwise there will be some TRC error later on, or off-grid errors. So 0.01 is sufficient. Click OK. So here you see the resolution of this snapping has decreased. So let me put my PMOS now. Press I, again browse. So from here, PMOS 18, put a symbol here. So this is my PMOS. So if I see the properties of this PMOS, it is seen that it is already 4 micron. This is because this tool generally remembers whatever the width that I have set in the schematic, whatever the last width that I have checked in the set in the schematic. So that's why by default the size of this PMOS is 4 micrometer. Now I have placed both the transistor. So if I go back and see my schematic, I need to do the following connection. I need to connect these 2 gates. I need to connect the 2 drains of the 2 transistor, like that. So for the connection of the gate, we'll be using the polysilicon. So if we zoom into this transistor and observe, we'll see certain things. So this red portion, this red layer, is the polysilicon layer, or it is the gate. So if I see in this layers option in the right side of the window, this GC represents this layer, the gate layer. So how do I know that whether this GC is this polysilicon gate layer, or it may be some other red layer, WN layer, it may be this red one. So to confirm this, what we can do is we can only display this particular layer. So only to display this GC layer, you can click NV, non-visible. So you see only the gate layer or the polysilicon layer is visible. If I press F, the polysilicon layer of the PMOS and NMOS are visible. Now I'll be selecting all visible. So now I am sure that GC is the polysilicon layer, and using the polysilicon layer I can connect these two gates. So the polysilicon layer is resistive compared to the metal layers. However, for short distance connection, like connecting the gates of the inverter or gates of some small circuit, it can be used, but preferably long connections should not be done using the polysilicon. If I observe, so this is the, you can see this is the drain of the NMOS and this is the source, or because the drain and source are symmetric, they can be interchanged. So we can create either of them as drain and source, so there's no harm in that. Now this cross mark is the contacts connecting to the drain and the metal one layer. So if you see here, this blue layer, if you see here, this blue layer is the metal one layer. So if I go to the layers and see this M1 DRW, because there are a lot of M1s, but if I see this DRW, so this is the metal one layer. So the contacts, the drain of the NMOS has already been connected to the this metal one layer. So if I just click this non-visible, so you can see that there are two M1 metal one layers on the above this source and drain. So this metal one can be directly used to access the drain and source of the transistor. So now so the conclusion is I'll be using this metal one layer for connecting the drains or doing the connection to the drains and source of the transistor, and I'll be using the GC or the polysilicon layer to connect the gates. So now let me zoom and let me draw the connection of polysilicon layer for connecting the two gates. Now to draw the rectangle, we have to select this layer with in the left hand side of the layer window, and we need to press R. So if you see here, the command is rectangle. Rectangle means I can draw any rectangle now with this selected. Just click at the edge and just draw. So you see I am able to draw a rectangle. So I have drawn a rectangle. Just click the mouse again. So I have drawn a rectangle which is perfectly aligned on the both sides of the gate, which has a very same size as this gate size. Now if I zoom out, I need to extend this layer till I reach the NMOS. So to extend, just press escape, so that my rectangle command is dismissed, or I'll be not doing drawing or rectangular drawing. Rather, I'll be stretching this layer such that I made the gate of this NMOS. So to do the stretching operation, just click on the blank layer such that no device is selected. So you have to make sure, press escape and make sure that no device is selected. Just right click and select stretch. If the device is selected and if you do this stretch, get this stretch command, it will not work. So make sure that you click in the blank area, right click and then select stretch. The shortcut option for getting the stretch option is S. So if I just touch this layer now by selecting the stretch command, this edge is getting highlighted. So it means that I will be able to stretch this layer. So if I just click and drag the mouse, so you see I'm able to stretch it. So I'll be just touching and overlapping a little bit this layer in the endmost region. Just click and then release it. So I need to undo the stretch command, so just press escape. So to dismiss any command, you need to press escape. Now if I zoom in this area, you will see that my gate is connected to this, but there is some little bit of misalignment. So I need to move this NMOS little bit so that it is aligned. Otherwise this may show some error in future in the design rule check. So just click this NMOS and press M. So I am ready to move it. So you see the command that I have selected is move. So the shortcut key is M. Otherwise you have to go to the tools or this is located edit M, move. So here the commands are there: move for copying, type C, for stretching S, and for delete simply delete key. So with the move command selected, just move it. Just click and the mouse once and then unclick it. So you see this drawing, the connection, the gate and this poly connection has been perfectly aligned with the NMOS device. So press F, so you can see the entire connection is done. So now I'll be doing the connection between the two drains. So again do the same thing but with metal 1 layer. So we need to go and select the metal 1 layer, M1 layer drawing, zoom in here and again do the same thing. Note that you see my snap spacing is little bit, I'm not able to exactly select the edge of this metal 1 layer. So maybe I have to decrease it to again 0.05, but it should not be lower than this, otherwise there will be off-grid error during the DRC. So this is the minimum possible resolution that is available in this technology. So you should not go lower than this. So this is the lowest snap spacing that is possible. Click OK. So you see I'm able to touch the edge now. So with this metal 1 layer selected, use the command rectangle and then start drawing the layer. So you just keep, by typing Shift Z, I'm just zooming in out and then I'm just drawing the rectangle. So this is almost aligned, little bit it's there but it should not create a problem. But better, the good practice is to stretch it and make it aligned. Yeah, so this is aligned and then again my stretch command is selected, just stretch it. So you see here also it is aligned. Save it. So now my this connection is done. So if I go back to my schematic and just check it, so I have done this connection, I have done this connection. Now I have to connect the bulk for both the PMOS and NMOS with the source, and then do this create these pins. So to do that, yeah, just select this NMOS, press Q. So if you go to this parameter tab, just scroll down and go to the show tab properties and click yes. So I want tabs for this transistor, and I have an option of whether I want these tabs on the left side or on the right side. So preferably, because I will be connecting this source with the tab, so I want these tabs to appear on the left side. So I want left tab. So click yes here, click OK. So you see a tab and tab, or sorry, this is P tab, which is connecting to the P substrate, has been arrived here. So now again, by using metal 1 layer, I can connect it with the source. So again, do the same thing, command with the command rectangle by pressing R, do the connection. So press escape, save it, press F, feed to the screen, then select the PMOS and do the same thing, press Q, get the properties, the parameter selected, go here, show tab properties. So here also I will be using tabs on the left side. So left tab, press, click OK. So the tab is visible here. Just zoom in and again do the connection between the two. This one between the two, between this tab and the source of the PMOS. So I think I am almost done. So I am ready for running the DRC, or the design rule check. So before design rule check, I have to again put the pins here. So VDD, ground, in and out. So it means that I need to apply signal here at this node as input, here at this node as output, here the VDD, and here the ground. So suppose if I want to tap I want to add a pin at this node, at this point. So the way to do is to label it, or labeling it. So because I'm going to tap from metal M1 layer, so I used to have that, I have to make label on the M1. So to do that, type M1. So it will show all the layers associated with M1. So for the drawing this layer, I have used M1 drawing, but for labeling it, I'll be using M1 label. So with this layer selected, create label, or the shortcut is pressing label. So use the current entry layer, or this layer, entry layer, and then I need to label it as, type the name of the label, OUT out, hide, and keep it, and just touch it here. So this, if you zoom in here, this plus button means that I'll be tapping the signal from this point. However, this level size is too big, so I will decrease this level size by selecting this level and then pressing Q and going here. The height is 1. Let me make it as just 0.3. So the size has been reduced. So now I'll be again creating the ground pin for this layer, metal 1 layer. so I'll be using the same M1 level. So again press L, get this window, and let me make this height 0.3. so I'll be using the C and D height. So ground, then I can zoom in here, the VDD, so press L, VDD. So I have made these 3 connections in the metal 1 layer, VDD, ground and out. Now I'll be applying the input at my gate. So note that this gate layer is different from the metal 1 layer. So I cannot use the same labeling for metal 1 to label the gate. So I need to go for the different gate layer. So as you remember, this is the GC layer. So I need to use the label for the GC layer. So if I type in here GC, you'll see that I have used this GC drawing for drawing this layer, and I have to use this GC label to label this gate. So you can press L, IN, height. So click here. So I'll be applying this input signal here, the output here, and VDD and ground.